Hello guys. Okay, so let me start first by making some comments regarding the homework. So basically, let me start with. The homework is long, so I need just to focus on a few things. For problem 9, it's a least square problem, and yes, I know that the general solution is basically the pseudo inverse, but basically, if you are minimizing a function that looks like this, right, then you want to differentiate with respect to x, okay, and equal to 0, and so we know the rule. You can know its proof, or you can just take it for granted that then you write a bracket that looks like this, and then when you differentiate this guy, it will gives you minus 2a Hermitian, and so this is equal to the all-zero vector. Then you will get basically, so this 2 minus 2 can go away, and then you get basically this equation, okay, and then now this thing is invertible. This thing is a square matrix, and because A is full column rank, then it is invertible. And so I can just write AX is equal to A Hermitian A inverse A Hermitian B. So basically this is a formula or an expression for the pseudo inverse. You can show that this is exactly the Moore-Penrose pseudo inverse in the case that your matrix is full column rank, but it's nice also to know it. Okay, so go for the pseudo inverse if your problem is very, very general and you really do not want to make assumptions. But in this problem, it is very specific, and it tells you that the matrix is full column rank, and so keep this in mind. It's useful even for you of you taking the wireless course. Things like this will will appear again and again. So this is important to have in mind. In part B, it's sort of the same thing. So basically, it's sort of, we are minimizing basically this quantity, right? But we know that x is a vector that is full of zeros except in one location. Okay, we don't know. If it's the kth location, then this is like xk, and every column in the matrix A will be multiplied by 0 except the kth column. So this is column k. So we are basically minimizing this thing, but we don't know k, and so we are also minimizing over, k. So the solution of this inner problem is, again, is something that you can write. Again, if we use this trick here, this is very important. So this will be minus 2a column k Hermitian, and then you have the bracket b minus a column k x of k. Okay, and so x of k, the optimal x of k, can be written as, so it is like this one here. It will be a column k Hermitian of multiplied by b divided by the L2 norm of a column k squared. So that's again a very explicit formula, and it is basically you take the inner product of the kth column with b, and then you scale by the L2 norm squared of the column. So this is a special case of this result here in part A. If your basically matrix is effectively, it is just one column. Of course, you are not done. What you can do is that basically you can plug in this x here and find which k will minimize. You can just do a simple search loop, and find which one will give you the minimum. Okay, so but keep this in mind, because later in the course I will give you something called orthogonal matching pursuit. And so it is a widely used algorithm for sparse signal processing. And most likely I will make you solve the homework problem first, and then we will discuss the convergence and stuff like this. But it is, it is sort of motivated by this idea that you can basically search, do searching, and if your unknown is just one component, you can basically solve this problem like this. So despite the fact that the A matrix is a fat matrix, but effectively you are solving a least squares problem, because you know that one component of x is non-zero and the others are equal to 0. Okay. What else? Problem 10. Like everyone insisted basically on assuming, for example, that there is a PDF. That the random variable is absolutely continuous, and so it has a PDF, or it's discrete, and so on. But actually, there is one part about a discrete random variable, but the other parts are very general. Okay, and so, for example, the first part, so you want the expectation of x, so you can basically write expectation of x, and then you introduce the indicators. Okay, so that's a common trick. okay, plus expectation of x, and then indicator that x is less than 0. Now, if we focus on this thing here, so this is basically, how can you write down something like this? We don't want a PDF or something, again, that basically tells you that your random variable is continuous or discrete or anything, because it can be anything. So here's the trick. You can write down this thing as expectation, integral from 0 to infinity, indicator x greater than, okay, so you can put here the 0, and this is less than or equal to, greater than, you choose a dummy variable of integration, u du, something like this. Let's see. What is this integration here? You are integrating an indicator, and the dummy variable of integration u is less than x, right? So here, if x is non-negative, if this is u, it's like you have a pulse, right? You have a pulse that is equal to 1 from 0 to x. So if x is positive, this will give you, this integral here with respect to u will give you x, which is this guy. But if x is 0 or negative, then basically, the indicator will be 1 when u is less than a negative number, but actually the boundaries of integration are from 0 to infinity, right? So you get 0. So this expectation here can be written like this, and this is a real very non-negative function. So you can apply to Nelly and exchange the expectation and integration here. Okay, and once you have the expectation inside, the expectation of the indicator is the probability. So this is probability that x is greater than u. You are done, right? So for the first part, here is the complementary CDF, and for the second part, you can do the same trick. And as you can see, no use of a PDF or anything like that. Okay, so I will try to later today or perhaps tomorrow. I will send you one of them. I think. This is the engineering. This is the engineering approach. This is the engineering approach. Okay, so we do these things because but like formally speaking, in probability, there is no such thing as this idea of combining, having things with the Dirac deltas and so on. And then there are like other types of random variables, singular. What about the singular random variable? Okay, you can say, well, we never encounter them in practice. No, I mean, we encounter them. Okay, so it's a long story, but the point is, if you can do your stuff without referring to a PDF or PMF, that would be much better, right? It would be much better. Your proof is general. You just use ideas. You are allowed to use CDFs because CDFs are defined for all types of random variables. Characteristic functions are defined for all types of random variables. Expectations and the rules. Use these things. CDFs, characteristic functions, and the laws of expectation. Linearity and so on and so forth. Okay, so much better than like basically confining yourself to to basically one type of random variable, because these proofs are general. And I will send you, I think, the proof of 10E. 10E is I will send you the detailed proof because it will be fundamental in proving the strong law of large numbers. So it is like sort of, we need to know it. Anyways, okay, so let's go now to our lecture, and I will start by a very, very, very quick review of Fourier analysis. So we start Fourier analysis by learning about Fourier series. Fourier series, you have a function from R to C. It is delta periodic, and delta periodic, of course, means that the function is, there is a non-zero big delta such that g of alpha plus big delta is equal to g of alpha for every alpha that is in R. And in that case, we call big delta, we say that it is the period. It is a period. Okay. Now, in this lecture, we will basically extend this definition to multiple dimensions. What does it mean to have like a 2-dimensional or 3-dimensional periodic function? Okay, these signals are very important. Like if you are doing image signal processing, images inherently are 2-dimensional signals. Okay, so what is the equivalent of this thing if your signal is multidimensional? Okay, so stay tuned. But for the 1-dimensional case, it's you have a non-zero parameter, and if there is a non-zero parameter such that g of alpha plus this parameter is equal to g of alpha for every alpha. Periodic functions are like sort of mathematical fiction. There is no function in reality that will look something like this, but the mathematical condition is that this should be satisfied for every alpha in R. Then your function is periodic. And under some conditions, there is no need like to basically delve into this big topic, but under some conditions, you can write down this nice formula for G of alpha, which is the Fourier series. And specifically here, I am just jumping directly to the complex Fourier series. So you can write down G of alpha in terms of the complex sinusoids that has fundamental frequencies k over big lambda. Okay, and the coefficients ck are given by the integrals, by those integrals, and those integrals involve an integration over a period. So you can start anywhere so long as you stop at basically, so you start at alpha 0, you stop at alpha 0 plus big delta. Okay. Now, it turns out, again, like if you, even if you do things like rigorously and define the Dirac delta like in a rigorous way, that there is a Fourier transform for the Dirac delta. Okay, so again, Dirac delta is a monster. It's not actually a function, but it turns out that there are several things that we do to functions, and they are also applicable to the Dirac delta. One of them is basically the Fourier transform of a train of Dirac deltas. The significance of this function is that if you want a mathematical model for sampling or converting a continuous time signal to a discrete signal, the way to go is that you imagine that the signal is multiplied by a train of Dirac deltas. So this function here is basically Dirac deltas. So this is the excess alpha, and we have a Dirac delta every big delta. Okay. So again, this function, it's like we need it. Okay, so to put it like this way, we need it. It is like we cannot do without it. Okay, and this function, if we now wear our engineering hats and we just pretend that it is a normal function, and we apply basically the formula for the Fourier series to it. So it is periodic function with period delta. So the coefficients, okay, so I suppose that we can do this Fourier series to the train of Dirac deltas. The coefficients will be 1 over delta, and then you can go from minus delta over 2, delta over 2. The most important thing is that you integrate over a period, and then you take the function here. The function here will be, so if this is 0, so you are basically integrating from minus delta over 2 to delta over 2. So you have one alone Dirac delta living here, and then you have e to the minus I 2 pi k over big delta alpha d alpha. And by the rules of the Dirac delta, basically this thing, if it's coupled with a function under the integral sign, and the function is continuous at 0, basically this Dirac delta evaluates the function at 0. So this will be 1 over delta e to the 0, which is 1. So it is 1 over delta, which is a result that does not depend on k. So if you take the Fourier, if you apply the formula for the Fourier series coefficients to the Dirac delta, you will basically get a constant that does not depend on k. It is always 1 over big delta. And so, again, if we take it as a matter of faith that the Fourier series is applicable to the train of Dirac deltas, then the train of the Dirac deltas is equal to its Fourier series expansion. Now here I replaced ck because we know it is 1 over delta. And so we get this nice basically relationship, which is not classical at all. So on the one side, you have a summation that looks like this, okay? And strictly speaking, this summation is not classical because if you think of this as a geometric series, it is not a converging geometric series because the magnitude of the ratio of the geometric series is 1. And for convergence, for an infinite geometric series, you need the magnitude to be strictly less than 1. So classically speaking, this is not wanted. This is not converging. But but again, like in terms of the Dirac deltas, this summation is equal to delta, and then basically the deltas like this. The Dirac deltas is spaced at every alpha. Okay, so again, this summation is important because like also it appears when you do something like the discrete time Fourier transform and so on. If you take the discrete time Fourier transform of the discrete time unit step function, you will have to use something like this. Again, it's very non-classical, but it is well defined mathematically. So at least, we will not do this, but at least we know that we are standing on, on a rigorous theory. There is a rigorous theory. And by the way, the rigorous theory was established, later. Okay, so people actually, physicists and engineers started using these things, and then later, Lawrence Barthes and other mathematicians basically justified basically why these things can be, or how can we understand these things. Okay, but for the purpose of this course, we will just take them for granted. Okay. Continuous time Fourier transform. Continuous time Fourier transform, it's a relationship between two guys, two functions. Each function, so here small g and big G, each function of them is defined on a domain R, and the function is complex valued. So each one of those functions, the domain is R, and the codomain is the set of complex numbers. And the CTFT is given by this integral. The inverse CTFT is given by that integral. So see here, the difference is that we have a minus sign here and a plus sign here. And the CTFT can be defined in a number of ways. And in this course, we will adopt these definitions. So if you use MATLAB or Mathematica to compute the CTFT, make sure that you make them do the CTFT as defined in this course, because their default CTFT is not what we have here. Okay, so make sure that but they allow you to change the parameters so that you can, for example, implement the CTFT as given in this course. Okay, what is the CTFT of the complex sinusoid? Well, if you have a complex sinusoid with fundamental frequency beta 0, the CTFT is a Dirac delta at beta 0. And, to show this, you can basically apply the definition of the CTFT, and you make use of this relation, or this integral here. Again, is not a classical integral, but it's very useful. So if you integrate from minus infinity to infinity, e to the plus or minus I 2 pi zw, and you integrate with respect to one of these two guys, let's say w, then this will give you a Dirac delta applied to the other guy, which is that. Okay, and for those of you taking wireless communications, basically we applied this thing like when we studied wireless channels. Okay, so it is very useful, and basically we can use we can define the CTFT for periodic functions. Okay, so for a periodic function, okay, so if you have a periodic function, it can be so for periodic function, so the function itself, suppose again it satisfies some conditions, so it has a Fourier series that looks like this if its a period is delta. Okay, and what we can do is that we can ask ourselves what is the Fourier transform of a periodic function. Okay, so you take the CTFT of g of alpha, and you will have to take the CTFT of an infinite sum, and the CTFT is an integral, and so you have issues of interchanging the order of integration and summation. But if this interchange is valid, what you can do is that you can apply the CTFT to each term on its own. So you can take the CTFT of this guy here, e to the I 2 pi k over lambda alpha, and this is a complex sinusoid at frequency k over big delta, and so the CTFT will be a Dirac delta at k over big delta. Okay, and so what we have here is that the CTFT of a periodic function is basically is discrete, like it's basically Dirac deltas in the frequency domain. Those Dirac deltas have an amplitude that is equal to the complex Fourier series coefficient. Okay, so now let's talk about one of the most important formulas, which is the Poisson summation, formula. Now, basically the idea is that start with this function. Okay, what is this function? It's some function. Okay, and you can check, okay, that this function here. Okay, so it's a function that is written in terms of an infinite sum. and suppose that this infinite sum makes sense. So for every beta, basically this summation is finite or anything like this. Then this function, if you replace beta by beta plus delta, you can by beta plus 1 over delta, you can show that this function actually is periodic. So this is periodic with a period 1 over delta. Now, if it's periodic, again, under some conditions, you can express it in terms of Fourier series, a complex Fourier series. So again, this function itself is called the periodization of big G, and because it's periodic, again, it's not for every periodic function that we can write a Fourier series, but assume that we can do so. So we can write a Fourier series, and we can compute the Fourier series coefficients. Okay, and if you compute the Fourier series coefficients, you can get a result in terms of basically the Fourier transform of big G. Okay, so the final result is very important. Okay, and it is this one here I will highlight. It tells you, okay, that, okay, so let me emphasize this result, that 1 over big delta summation n belongs to z, g of beta minus n over delta. So this is our starting function. Once you do the complex Fourier series and obtain the coefficients, you will find that you will get that this thing is equal to summation m belongs to z, the set of integers, g of m delta e to the minus I 2 by beta m delta. And what is the small g and big G? They are basically related through a Fourier transform relationship. Okay, so what is going on? What is this thing? So suppose that you have a function, so g of alpha is an underlying continuous time function. Of course, the variable alpha does not need to be time, but the language we use, the term that we use is that it's continuous time. Okay, but it can mean anything, even some abstract variable. So g of alpha is an underlying continuous function. And so what is g of m delta? So g of alpha is an underlying continuous function that is, you can say, evaluated, or you can say sampled every big delta. So that's g of m big delta. And it is multiplied by e to the minus I 2 pi beta. Okay, so beta is this variable here. Beta is the same guy here. M big delta, and delta is a positive parameter. Okay. On the other side, we have big G. And what is big G? Big G of beta is the CTFT of G of alpha. Okay. So you have a function. So basically, we have a function and its Fourier transform appearing in this peculiar way. On the one side here, we have the function in the time domain sampled every big delta. And in fact, this quantity here is by definition the DTFT of the sequence G of m delta. So the DTFT of this is given by another infinite sum involving the continuous time Fourier transform of G of alpha. Shifted. Okay, so basically this is G of beta minus 1 over delta, G of beta minus 2 over delta, and so on. Basically, n takes all integer values. So this relationship again is very important in a number of ways. One of them is that you may look here and say, well, we typically have an infinite sum on the right and an infinite sum on the left. However, one of those two sums may be very manageable, and you can actually get it in closed form, while the other sum like looks intractable. So basically you can use the Poisson summation formula again, because like you suppose that you want to compute the DTFT of some signal, so you are stuck with this summation here, and you find, like, for example, the G is the sinc function, and then you put G equal to sinc, and then you have a summation of sinc multiplied by complex exponential, and it seems to be intractable at all. So the Poisson summation formula tells you that you don't really need to compute this thing. What you can do is to compute another summation which involves the Fourier transform of this small g. Now, the Fourier transform of sinc is rect, so basically you find that the summation involving the sinc and the complex sinusoids becomes a summation involving rect, which is basically very manageable, and you can actually plot it like it's like a square wave if basically those rectangular pulses are not overlapping, and so on. So one advantage of the Poisson summation formula again is that sometimes one of these two sums is very manageable. In fact, you can actually write it in closed form, while the other is intractable. And so you can use the Poisson summation formula to evaluate infinite sums. You can use it to obtain discrete time Fourier transform, and so forth. Okay, so this Poisson summation formula is something that you should keep in mind. Okay, and of course you learn how to use, because again it requires that you involve in it basically a Fourier transform pair. Okay, now. Okay, so before proceeding, actually, this mysterious Fourier series of a Dirac delta is a special case, right? So let's talk about this special case. So suppose that G of beta is equal to delta beta. So suppose that here we have a delta, okay? So what is the inverse Fourier transform of delta of beta? Okay, so the inverse, what is the function that if you take its Fourier transform, you get Dirac delta of beta? It is 1 everywhere. So basically here, CTFT inverse, and you get G of alpha is equal to 1. So now if you rewrite here, you'll find that 1 over delta, summation n belongs to z, and then you find here delta of beta minus n over delta. This thing is equal to summation 1. So basically this function is 1. If you sample it, if you evaluate it every big delta, you still get a 1. So you just have a 1, and then you have the complex guy here, which is minus 2 pi beta m delta. Okay, so it is very close to what we have above, perhaps after replacing m by minus k or something like this. But the Fourier series of a train of Dirac deltas basically is a special case of the Poisson summation formula. The discrete time Fourier transform, it's applied to sampled signals, or basically to discrete time signals, or what in math you call sequences. Those sequences are now defined on a grid. Okay, so the Fourier transform is from R to C. The discrete time Fourier transform is from Z to C, because it's basically you have a function that is defined on the grid NTS, where TS is a positive parameter, and basically you assign corresponding to each n, you have a complex value. The discrete time Fourier transform, it's defined like the continuous time Fourier transform, but it is adapted basically to a discrete signal, and so rather than an integration, it has a summation. And in the e to the minus I 2 pi f, rather than having ft, it becomes nts. One very important thing to remind you of, okay, so I will write it here, DTFTs are periodic. Okay, by definition. Okay, so x of f is defined as summation x of nts e to the minus I 2 pi fn f of nts. Okay, and now define fs to be 1 over ts. What is x of f plus fs? So it is summation x of nts e to the minus I 2 pi f plus fs nts. Okay, now you can split this exponential into this one here, which is the original one, and then there is an extra guy, but by definition fs is 1 over ts, so this is 1, and you have e to the plus or minus I 2 pi times an integer. This is equal to 1, which means that x of f plus fs is equal to x of f. So by the way the discrete time Fourier transform is defined, so again, like, take it for granted, our ancestors defined the Fourier transform of a discrete time signal as you take the samples of the signal and you multiply each one by e to the minus I 2 pi f, so f is the frequency variable nts, and then you sum over n. Now if you define anything as such, then by definition the reciprocal of ts, which is fs, which is called fs, typically called the sampling rate, it will be a periodic function. Okay, so DTFTs are periodic, and you know, can you take the DTFT of a discrete time signal that is always equal to 1? So all the samples of the signal are equal to 1. Now, if you try to do this discrete time Fourier transform, you will find, so okay, so all the samples are equal to 1. Then you have basically this summation. And again, this summation is not something that is classical, right? You are summing e to the minus I 2 pi f nts from minus infinity to infinity. What is this thing? It is exactly what I talked about, here, right? So basically, this summation here is a train of Dirac deltas that are spaced by fs, where fs is 1 over ts. So again, the train of Dirac deltas is like fundamental, and we just have to make good use of it, and it is what we employ to model a signal being converted from continuous time to discrete time. The discrete time Fourier transform, it has many properties. So on Blackboard you find the table of properties, and at this stage, basically, proving each property is not the issue, but actually making use of each property is very important. So you have, the conventional properties. What will happen if you time shift the signal? What will happen if you have a convolution in the time domain, so it becomes a product in the frequency domain, and so on. So these properties, again, regardless of their proofs, you need to basically refresh your knowledge about them, because they are very useful. And the nice thing is that many of these properties, if we start dealing with multidimensional signals, they also hold. Okay. So, any question? Okay. The inverse DTFT, it's basically defined in terms of an integration, and basically, if the inverse DTFT, the way I like to do it in a course on signals and systems is that since the DTFT by definition is a periodic signal, then basically you can apply to it the formula for the complex Fourier series. Okay, and so you can sort of, if you do like rigorous proofs for the Fourier series, now the DTFT becomes a matter of applying those formulas once they are valid. Again, we can exploit here this important fact that DTFTs are periodic. Okay, or you can just take that this is the formula for the inverse DTFT. DTFT over convolution, convolution becomes a product. This is true also for the CTFT, and this is one of the very important uses of Fourier analysis. Why is convolution important? You can think of two things that makes convolution like very important in the life of an engineer or a statistician or something. So can you come up with basically where is like the process of convolution emerge? Filtering. So for exactly linear time invariant systems, if you study them, you find that their output is defined, is derived. So once you define what a linear time invariant system is, then you discover that actually the output is the convolution of the input with the so-called impulse response. So many systems, in fact, linear time invariant systems are a fiction that does not exist in reality whatsoever, but they are a very good fiction in the sense that many practical systems can be approximated very well as LTI systems. And so we need to basically compute their outputs, and we need to do convolution. But convolution is like, you need to do the convolutional sum or convolutional integral, which may not be that nice. So you can basically work in the frequency domain where you don't need convolution, you just need to do product. Okay, you just multiply things together. Another thing, convolution also appears in a very, very important subject. So other than linear time invariant systems, something great in probability. If you are interested in the distribution of the sum of random variables, exactly, sum of random variables. Okay, so once you sum random variables, if they are independent, then you find actually, so you can basically start giving, what is the CDF of a sum, and then you convert it into PDF, and then you discover that if your random variables are independent, then the formula for the PDF of the sum is exactly, the convolutional, the convolution integral or convolutional sum, depending on whether you are doing discrete or continuous random variables, which is very important. In probability, and actually in this course, we will deal with sums of not just two random variables, but many of them. In fact, we will take the limit as the number goes to infinity, and so convolution becomes like sort of intractable. Like you have to take basically two random variables, convolve their PDFs to get the PDF of the sum, and then convolve this with the PDF of the third random variable, and so on. It becomes impossible to deal with, again, if you are talking about sums with a huge number of terms, perhaps infinite number of terms. So the way to go is to do Fourier analysis, and basically in probability, Fourier analysis is basically, what is the Fourier transform of a distribution? It is the characteristic function. Okay, so like in proving central limit theorems and so on, we make use of the characteristic function because of this very important property. It, rather than doing convolution, you basically do a product. Okay, DTFT of a periodic signal. Okay, so suppose that you have a discrete time signal and it is periodic. What is its DTFT? So I will do this one. I mean, you say, why? I mean, everything else you say, okay, just, you can take it for granted. But the DTFT of a periodic signal will be very relevant to this course. Okay, because in this course, there will be, the topic of the DFT. So the DFT is a Fourier transform sampled, of a signal that is sampled in time and sampled in frequency. And so it turns out that the DFT is very related to the DTFT of a periodic signal. Okay, so this one, let us actually go through the steps. Again, because it will come to us, and actually the relationship can be exploited. So I can give you like a very evil DFT, and you don't know how to compute actually it. And actually, the way to go is to use the DTFT. So you can actually use the DTFT to compute DFTs and so on. Okay, so this will become clear later when we define what the DFT is. Okay, for now, suppose that you have a discrete time signal. It is periodic. Its period is big N. You are interested in its DTFT. First order of business, okay, write down the definition of the DTFT. It is given by this summation here, x of n e to the minus I 2 pi f n t s. Okay, then what you do is that you rewrite this infinite sum with one summation index using two indices. Okay, so basically, I mean, this seems like complicating things, but in fact, it will simplify things if we exploit the periodicity. Okay, so rather than having one summation, so this is a sum over the integers. Rather than doing this, I will do something else. I will do a summation L from minus infinity to infinity, and then summation, another finite sum from 0 to n minus 1. Here we have x of n, but here I have x of n plus L big N. So are these two things equivalent? Yes, let's see. So basically, if big L is equal to 0, then small n goes from 0 to big N minus 1. So small n runs from 0 to big N minus 1. Okay? What if big L is equal to 1? Small L is equal to 1. If small L is equal to 1, then this guy becomes big N, and then you add small n, which goes from 0 to big N minus 1. So n now will go from n to 2n minus 1. Now what if L is 2? Then this term here becomes 2 big N, and when small n goes from 0 to big N minus 1, this will go from 2n to 3n minus 1, and so on and so forth. And then L can be minus 1. And you will find that basically this double sum takes care of every integer value. Okay, but you are writing it in such a way, and by the way, this trick will be very useful in implementing the DFT efficiently. So never underestimate it. Like again, it looks like, I mean, you have just one summation index. Now you are converting it into two. Yes, sometimes this is the way to go, and actually it leads to very nice understanding of, very nice proof, or very nice basically derivation of an algorithm or something like this. So the idea here is to, we want to sum over the integers. We will do it via two sums. One of them is also over the integers, and the other one is a finite sum from 0 to big N minus 1. Note that big N is not, generally speaking, you can choose big N to be any positive parameter, but here we will choose big N such that it's the period. Okay, it's the period. So what is the advantage of something like this? Now look at this thing. Signal x itself is periodic with a period big N, so this is equal to x of n. So this thing here will no longer be dependent on the index small l. It will just depend on small n because of periodicity. Okay, so this will allow us to basically rearrange the terms, because now the only term that depends on a small l will be basically this exponential. There is a small l here, but now this is no longer a function of a small l, because the signal shifted by integer multiples of its period is exactly equal to the signal itself. And so this, we lose here the dependence on n, which is nice, because now we can take the stuff that depends on n, and there is only one summation that depends on small l. And again, what is this summation here? What is this summation? It is not a classical sum, but it is a friend of us now. I mean, you must get used to basically this summation. It's so important in signal processing. And so it is e to the I 2 pi f l. So that's an index going from minus infinity to infinity. It's an integer, and then a positive parameter. Okay, so according to the Poisson summation formula, or the Fourier series, or whatever, you can understand it in a number of ways, but this is now given by an infinite sum. This guy appears here as a reciprocal, and then you have delta, and then you have this variable here, f, minus, if we call this index here, I called it here, what, L, so L in Z, and then you have L over this thing, N over Ts. Okay, so this infinite sum is very important, and now you can express basically things in terms of the Dirac deltas. And now you rearrange the terms again. Okay, so you play with the terms again and use this nice property of a Dirac delta that, you know, the Dirac delta, if you multiply by a function like this, it evaluates the function at the quote-unquote the location of the Dirac delta. Okay, and so basically those Dirac deltas, you know, can basically evaluate f. So this f here can be replaced by the location of the Dirac delta, which is LFS over n. And so you end up basically with this dtft of a periodic function. Okay, so the dtft of a periodic function, it is basically Dirac deltas that are separated in frequency by fs over n. Fs is 1 over ts, and n is the period of the discrete time signal. And there is an fs over n here, okay, which is, you know, just a scale, an amplitude scaling factor. And then there is something, okay, here, which is this finite sum with n terms, which is given exactly by this thing. Now, it, you know, later, you know, perhaps in, you know, in 2 or 3 lectures, this summation here is the dtft of x of n. Okay, so later we will know or recognize this. We will recognize this as the dft. Okay, so you know, for now it's just a sum, and it may appear that it's like meaningless, or you just to go and compute it and then what, but actually it is the dft, and again this is a story to be told. Of course, I mean, from homework 1, perhaps there was a problem in which you used Parseval. So Parseval, again, it's something like the Poisson summation formula, in the sense that you have 2 things. Okay, so for example, for discrete time signals, you can have this summation, and you can write down this summation in terms of the dtft of x1 and x2. So you have a sum of things in the time domain, and you have an integral of the dtfts. And why is this good? Well, again, same story of the Poisson summation formula. Sometimes this summation is manageable, this integral is evil, and so you can basically evaluate the sum and know the integral, or vice versa. Sometimes this summation is evil and the integral is so easy. Perhaps you are integrating rectangular pulses and you get the value, and it will be the value of the sum. Okay, so generalized Parseval is also an important aspect of Fourier analysis. And you know, again, like here, we will basically make use of it. Okay, any question? Multidimensional signals. You cannot do signal processing. Again, you cannot just do signal processing to single, you know, the signals in 1 dimension. What about images? I mean, digital image processing is a big branch of signal processing, and basically the objects there are 2-dimensional signals. Generally, you can have n dimensions, and of course, as we know from signal processing for 1-dimensional signals, the Dirac delta is important to us, and so it is also defined for multiple dimensions. And so if I write down delta t, so now t is a vector with components t1 up to tn. So we have n dimensions, and the Dirac delta is basically a Dirac delta of each dimension. Okay, so it is delta of t1, delta t2, and delta tn. Okay, so but as a compact form, I will just write it as delta of t. So the Dirac delta of a vector, or basically n dimension, it is as if you have a Dirac delta of t1, a Dirac delta of t2, a Dirac delta of t3, and so on. It's the functionality of the Dirac delta, you know, that basically when it's coupled with a signal under the integral sign, and it gives you the value of the signal at the origin, is same story here. So basically, if you have a multidimensional Dirac delta multiplied by x of t, so long as x of t is continuous at t equals 0, then it will give you x of 0. Okay, note that I write it x of 0 here, but actually it is x of 0, 0, and 0. Okay, so again, here we use like basically compact representation, which I can write things as x of t, but you understand like in the context that actually it is like x of t1, t2, t3 up to tn, and so on. Shifts can be understood in a similar way. Again, a Dirac delta, a multidimensional Dirac delta is basically Dirac deltas multiplied together, and in Dirac delta, of the same variable, I mean, it is not allowed to multiply Dirac deltas. Okay, so basically delta t1 is not defined. Okay, so but what we have here is does not contradict the general rule, because those are different variables. Okay, so Dirac deltas of different variables, it's okay, and we can basically stack them to multiply together like this. But what is not allowed is like you have a Dirac delta, of t1 and then of minus t1 or any other thing involving t1. The Fourier transform of a multidimensional signal is defined in this, this integral here. So the Fourier transform of a one-dimensional signal, it takes you from t to f. Now it takes you from t1, t2 up to tn to f1, f2 up to fn. Okay, so the multidimensional continuous time Fourier transform, it takes, you define it, so it takes a function, so x is a function from Rn. Okay, now big X also will be a function from Rn. Okay, one of them has the variables t1, t2, and tn, and the other is given by the inverse CTFT, and it's parameterized by f1 up to fn. Okay, and on Blackboard you find these notes on two-dimensional signals, and in two-dimensional signals it's nice to understand what does it mean like to have a sinusoidal signal in two variables. Like it's nice basically to have this understanding, or you can just take things as abstract and say, okay, it's just a function x of f1, f2, and so on. But if you want like to visualize things, you can actually visualize at least sinusoidal signals in 2 dimensions. But the moral of the story is that now the Fourier transform, you have a function that depends on 3 variables, then you should generate a Fourier transform that depends also on 3 variables. Okay, and in a compact form, rather than writing e to the minus I2 pi f1 t1 plus f2 t2 plus f3 t3, you can just write the f vector transpose multiplied by t, because this thing here is f1 f2 up to fn multiplied by t1 up tn, and this will give you the summation here. The integral that I talked about in 1 dimensions is also here. Okay, so basically if you have integral, it can be plus or minus, by the way, I2 pi, and then you have the inner product of 2 n-dimensional vectors, and you are integrating with respect to 1 vector. Okay, so this is, again, if you read something like this, it's a shorthand for this. N integrals plus or minus I2 pi u1 w1 plus u2 w2 plus un wn, and then if you are integrating dw, it means this dw1 up to dwn. So what is this? It will give you delta u1, delta u2 up to delta un, and so this can be in shorthand written as delta of u. Okay, so so these properties also hold in multiple dimensions. Okay. Challenge now is what is a periodic signal in multiple dimensions? So a signal, basically defined on t, and t is an Rn, is periodic if there exists n. So if you are living in 2 dimensions, you need 2. 3 dimensions, you need 3. You must have n linearly independent vectors, P1 up to Pn. And for each of those vectors, we have x of t plus Pn. Remember that t is an n-dimensional vector, and Bn is an n-dimensional vector, is equal to x of t for every t that lives in Rn. And this should be true for every n1 up to n. Okay, so again, you have a periodic signal, let's say a two-dimensional periodic signal, if you can find two linearly independent vectors, and I will give you examples shortly, such that if you are at a point in the two-dimensional space, generally in the n-dimensional space, if you move along one of those n linearly independent vectors, you go to a value of the function that is exactly equal to x of t. So x of t plus Pn is equal to x of t. This should be true for any one of those n linearly independent vectors. Okay. So now things are like a bit complicated then, like in one dimensions, it's like xt plus delta is equal to x of t for every t in R. Now, if you want periodicity in n dimensions, you need to find basically those vectors, right? And so, you know, what can we infer if this is true for every t and for every n? What about x of 2 plus t plus, you know, let's say an integer multiple of 2bn? What is this thing equal to? What if you take this vector and you just scale it by 2? X of t, exactly, because you can think of it as px plus pn, and you know, this thing, you know, according to the original definition, this is like x of t plus pn, which again from the original definition, this is x of t. Okay, and so you can actually generalize basically this expression here and write down this very important expression. So you can define something called a periodicity matrix. What is a periodicity matrix? You take your n linearly independent vectors and stack them as columns in an n by n matrix. Each one of those vectors has n components. You stack them together and you have an n by n matrix. It's called the periodicity matrix, and because by definition those columns are linearly independent, this matrix is invertible. Okay, now we can basically take the main definition of periodicity in multiple dimensions and say that if I take t, if I take the periodicity matrix and multiply it by m. Okay, so what is this thing here? M is a vector of integers. This is just p1 multiplied by m1 plus p2 multiplied by m2 plus b3 multiplied by m3. Those are integers, and the b's are our vectors defining, you know, the periodic signal. So this will be x of t for every t living in Rn. Okay. Now, for n-dimensional periodic signals, we will define something like, because the signal repeats itself, so there is like a unit that repeats itself. There is a cell or a fundamental parallelepiped. Okay, so it's called a cell. You know, sometimes I just call it a fundamental cell or fundamental parallelepiped. And what is basically this thing? If you have a signal parameterized by the matrix P, so now periodicity is captured not just by the scalar delta, it's captured by an n by n matrix. Periodicity in n dimensions require n by n matrix. The columns are basically directions. If you move in these directions, basically you get the same value of your function or of your signal. X of t plus Pn is equal to x of t. So the fundamental cell is basically this set here. It's a set, you know, the set of points in the n-dimensional space. You start at some point, and then you move along basically the vectors, the b vectors, with steps, that are between 0, 0 included, up to 1, and 1 is not included. Okay, so let me again write down what is this thing. So here we are talking about the points in the space satisfying that T can be written as some starting point, and typically we can put this equal to the origin. But I mean, it's also useful to keep it general, plus, and then you have here a very particular thing. It's P multiplied by theta. What is P? It's, the matrix, the periodicity matrix containing those vectors that define periodicity, multiplied by theta. And so what is theta? Theta is a vector living in Rn also. Each component in theta is from 0 up to 1, with 0 included and 1 not included. Okay, so what is this thing? So now it's time for an example. And basically, multi-dimensions are like sort to visualize, unless like we are talking about 2 dimensions. So I will make my example 2-dimensional so that we try to understand what are these things based on, and something that we can visualize. Okay, so my function will be, so T1, the T1, T2 plane is the plane of this page. So this is the direction T1, this is the direction T2. And so what is the function x of t? I will define the function x of t. Of course, it needs a 3rd dimension. But rather than plotting something that is 3D, what I will do is that I will do these shades. So x of t1, t2, so that's x of t. So I will go to the t1, t2 plane and I will shade it. If above the black parts, x of t1, t2 is equal to 1, and over the white parts, it is equal to 0. Okay, so again, what you see here is like as if you are looking to the T1, T2 plane from above. And there is a function defined over T1, T2. But rather than basically, doing things in 3D, what I will do is that if x of T1, T2 is equal to 1, I will basically paint in black. Otherwise, I will paint in white. So if you look at this figure here, you understand that there is a function defined on T1 and T2 plane, and this function is 1 over this point here, this point, this point, this point. The function is 1, and it is white over the other, it is 0 over the white parts. Okay, so is this function periodic? And so this pattern goes on forever in all directions. Is this function periodic? And well, the question is, can you give me 2 directions that are linearly independent, so they cannot be parallel? Can you give me 2 linearly independent directions such that if I move along any of these 2 directions, I will reach the same value of the function? Okay, so basically the vectors of periodicity are not unique. So you can choose B1 and B2 to be like this, right? So look here, the vector B1 is this vector. Okay, so it is this vector, right? Now, if you are this starting point, if you move in this direction, if you move along this vector exactly, you will reach a point at which x of t is the same as at the starting point. And this is applicable to any point in the 2-dimensional plane. If you move in that direction, you will find that the function, x of t plus p1 is equal to x of t. And another vector here, p2. Okay, so this is a vector that is clearly linearly independent of p1, and it satisfies the same thing, that x of t plus p2 is equal to x of t. So basically, each one of those figures is like a is like a parallelogram, okay, and it has this is A and this is B and this angle is alpha, and so B1 vector you can write it as 2A and 0. Remember that this is direction T1, and above here is is direction T2. Again, this thing here is something living in the two-dimensional plane. So the T1, T2 plane is the page I'm talking about. And again, I am just shading to indicate that there is a function defined on R2, and this function is 1 over black parts and 0 over the white parts. Now, this function, again, is periodic. You can find the B1 and B2. B1 can be equal to A and 0. And B2, which is this red thing here, it can be written as 2B cosine alpha, 2B sine alpha, because, again, this angle here, this angle is alpha. Okay, so this is one periodicity matrix. But you can say, well, what if I take B1 like this? But also if I move along this red direction here, I will also satisfy the definition of periodicity. If you start at any point and move along the vector B2, you will reach a point at which the function x has the same value. Yes, and here are two other directions. Okay, so in other words, you can come up with many, perhaps infinite number. It's not unique. The periodicity matrix associated with a multidimensional periodic signal or function is not unique. And which one of them is useful? Again, for me, it's like what makes the problem easy in terms of you're computing things. We'll see. I mean, we do the Fourier series and so on. So you basically need whatever is convenient. So what about the fundamental cell? What is the fundamental cell? So the fundamental cell, if you choose these two guys as your vectors B1 and B2, this is the fundamental cell. Remember that what is the fundamental cell? In 2 dimensions, it's B1, B2. So this is our periodicity matrix multiplied by theta 1, theta 2. And so basically, we are talking about the vectors. If we choose T0 to be equal to 0, 0, this is theta 1 B1 plus theta 2 B2. Okay, so basically the fundamental cell is that you move along B1, you move theta 1 along B1, you move theta 2 along B2, and those thetas are numbers between 0 and 1, 0 included, 1 excluded. So basically, if you do this, you will cover this green part here. Okay, the boundary, this is not actually included, but you understand it from the definition, not from the drawing, that basically theta 1 and theta 2 are between 0 and 1. And the fundamental, this cell or fundamental cell, you can think of it as it's something that you can, by shifting it, you can basically tile the whole plane. Okay, by shifting it, you can tile the full 2-dimensional plane, and in n dimensions, it will cover the full n-dimensional space. Okay, so in the case of choosing B1 and B2 as such, this will be the fundamental cell, and here this will be the fundamental. So the fundamental cell, like in 2 dimensions, again, it's like you have this is B1, this is B2. The fundamental cell is basically this thing here, but this boundary is not included. Okay, so this and this are not included, but the others are included. And basically, in 2 dimensions, what is this shape? It's a parallelogram. Okay, so that's the name, parallelepiped. In the old days, parallelepiped was a term that is used in 3 dimensions, and in higher dimensions, people used parallelotope. But I think in the modern literature, parallelepiped is used like in n dimensions. Okay, but like in the old days, this thing was like it's like parallelograms in 3 dimensions. But now it's generally used. If you don't like it, there is also parallelotope. Something like this. Okay. Okay, so the fundamental cell again is like this, basically it has a volume. Okay, so I will use the term of volume. Okay, but by volume here, this volume is volume is length in 1 dimension. It is area in 2 dimension. It is volume in 3 dimension and so on. But I will, in many cases, I will just use volume and you understand what actually I'm talking about based on the dimensionality. Okay, so here you can say, well, it's an area, right? The area of the fundamental cell, but again, you know, it's a volume. If you just want to make a statement that is general, and with the understanding that if our function is basically in 2 dimensions, then we are talking about area. The volume is given by something very nice related to matrix B. So if you want basically the area of this thing or this thing or this thing, you go to the P matrix, you take its determinant, and you take the absolute determinant. And so this is sort of a geometric interpretation of the determinant. You know, so what is the determinant of a matrix? You know, if the matrix has linearly independent columns, so you can interpret the, you know, the columns of the matrix if they are like geometric vectors in the n-dimensional space, and they define a parallelepiped, and basically the absolute value of the determinant will be the volume of that thing. Okay. Now, like in 1 dimensions, you may define something called the fundamental periodicity matrix. And in that case, you try to describe your multidimensional periodic signal using a P matrix with the smallest possible magnitude determinant. Okay, this may exist or not. Okay, so it may not exist. Give me an example in which basically there is no fundamental periodicity matrix. A constant signal, right? So if you have a constant signal, so if x of t is equal a constant, okay, then basically any vectors of any length will work. Okay, so basically a periodicity matrix can be, let's say, epsilon 0, 0, epsilon, right? So, you know, it tells you, you know, basically, if you move in the t1 direction by epsilon, the function is the same. And if you move in t2 by epsilon, the function is the same. Well, the function is constant. It's constant everywhere. So what is the volume of the fundamental cell? It's epsilon squared. Well, I can choose epsilon as small as I wish. Okay, so the minimum may not exist. Okay, but if the minimum, if for some signals the minimum may exist, and in that case you say that your matrix is the fundamental periodicity matrix. So it is a generalization of the concept of a fundamental period. So there is a period, okay, and then there is a fundamental period that is not defined for all periodic signals. It is defined for a special class of signals. Okay, so the same story here, and you can find something called the fundamental periodicity matrix. But the good news is, like, if you want like to do the Fourier series and so on, you do not really need to find this guy. The Fourier series is, you know, give me a P matrix and I can do the Fourier series. You do not really need to go and obtain the fundamental periodicity matrix, which has the determinant with minimum magnitude. Any question? Okay. So we started today's lecture with the Fourier series in 1 dimension. So in multiple dimension, the Fourier series is this thing. Okay. So it is a summation with n infinite sum. So basically, it is a sum. I write it here as one sum, but actually it is like this: k1 in z, k2 in z, kn in z, and then there are coefficients that depend on those guys. I write here as ck, but actually it's ck1 up to ckn. And then there is the complex exponential. Now it is in this form, e to the I2 pi. In the 1-dimensional case, there is the index of summation over the period. Now what do we have? We have basically a vector of those indices, kn. So it's big K transpose, and then P inverse. Okay, and so of course, like, we need matrix P to be invertible, T, and so T is T1 up to Tn. Okay, so it looks, it looks a bit complicated, but this is basically the generalization of the Fourier series to multiple dimensions. The coefficients become dependent on basically on they are a function of n indices. Okay, and you obtain them with an integral. Okay, so what is the integral now? I will just give you the formula. So this is the integral for the Fourier series coefficients. Okay. So you know, if we like try to basically do the proof, you know, it's not very rigorous, but the idea is this: you write down this formula, okay, and then what you do is you say, okay, I will take x of t and multiply it by exponential minus I 2 pi m transpose b inverse t, where m is a vector of integers in the n-dimensional space. So you multiply left and right, okay? So when you multiply, so this one will be ck, and then you multiply, it will be e to the I 2 pi k minus m transpose b inverse t, okay? And then what you do is that you integrate, okay? So you integrate both sides, and you will do the assumption that you can integrate term by term, and so you integrate this thing. You integrate over a fundamental cell, okay, fundamental cell, okay. And so what is this integral over a fundamental cell, okay? And we will take the fundamental cell basically to be centered, okay? So let's take a cell with t0 equals 0. Remember, what is the definition of a fundamental cell? It's the set of points in the n-dimensional space that can be expressed at t0, which I will take to be 0, plus b theta, and theta is the vector, you know, where each component is between 0 and 1. Okay, so I will integrate over basically a fundamental cell, and I will do a change of variables here. Let t be equal to b theta. So it's basically going. So here I am doing a change of variables from basically t1, t2 up to tn to theta 1 up to theta n. Okay, and of course, if you do change of variables in a multidimensional integral, you need to basically have a Jacobian, and so you have a Jacobian here, and the Jacobian, if t is p times theta, then basically the matrix of partial derivatives between the t variables and the theta variables will simply be the elements in matrix P. And so basically the Jacobian, you know, the absolute determinant of the Jacobian will be the absolute determinant of matrix P itself. Okay, so this is the Jacobian, you know, as you know from your multivariable calculus class, and then you have the d thetas. And you can now, so if t is equal to b theta, then b inverse t is equal to theta, and now we have an integral that looks like this. Okay, so the trick is that you know that basically the values of t on a fundamental cell are satisfied that p is, you know, once you choose t0 to be equal to 0, t is equal to b theta, then rewrite your integral in terms of the theta variables. And the nice thing is that you don't have this evil B inverse matrix in the exponential. Now, basically, B inverse, once you replace T by B theta, B inverse will eliminate the B, and you get basically integration in which you, that is like sort of straightforward in terms of theta 1, theta 2 up to theta n. And you can see basically that all of those integrals, of course, each theta is between 0 and 1. All of those integrals, you know, they will give you basically this determinant here. If each k matches each m, so if big K is equal to big M, otherwise you will get a 0, and then and so this means that the nth coefficient. Okay, so basically again, like you multiply this thing, you integrate, so you will find that basically this integral is 0 if k is not equal to m. So you have an infinite, you know, an infinite terms here for each possible k vector, but for all those vectors, if k does not match m, then you get a 0. But if k is exactly equal to m, then this integral will give you the absolute determinant of matrix P, and so each Cn coefficient, you know, is given by this. So this is a generalization of this formula 1 over delta integral t0 plus delta of the function in 1 dimensions e to the minus I 2 pi, 2 pi, m over delta t dt. This nice thing, now it becomes this thing. It's an integral. So in one dimension, we say that we integrate over a period. Okay, so you start your integration somewhere, you should move by a period. So here the way of saying it, that we will integrate over over a fundamental parallelepiped, okay, or a fundamental cell. Now the factor here that we have in the one dimensional is 1 over delta, 1 over the period. Here it's no longer a period. Now it's a periodicity matrix. Okay, and what we scale by is basically 1 over the absolute or determinant of matrix P, the periodicity matrix. And then you have e to the I 2 pi m transpose P inverse T. Okay, so things are getting much more interesting in multiple dimensions. Okay, so what if you want to sample a signal that is multidimensional? So in one dimension, if we sample every TS, we multiply x of t by the train of Dirac deltas. Okay, so this is something that you learn in courses like signals and systems, digital communications, and so on. So you do this thing to model basically sampling, taking a sample every TS. Now our signal is multidimensional, so we will multiply by Dirac deltas, but those Dirac deltas basically they are characterized, they have a pattern, so they exist in the n-dimensional space in a pattern that is specified by a matrix Q. And so V is a vector in the n-dimensional space, and now you just want Q to be an invertible matrix. Okay, periodicity, since it's a periodicity matrix by definition, it must be invertible. Okay, so I mean, what do I mean by this? I mean, so how do we sample multidimensional signals? The easiest type of sampling is rectangular sampling, which is like this. So your Dirac deltas exist. So basically those dots here are the locations. So the dots are the locations of the Dirac deltas. So you can basically put your Dirac deltas on a rectangular grid. So rectangular grid, it means that, basically the separation along T1 is just a fixed number Tx, and along T2 is just a fixed number Ty. And so those are your Dirac deltas, and in that case, the Q matrix is just a diagonal matrix with parameter Tx here and Ty there. But who say that this is actually, the way to go? We can have any pattern in the two. I mean, in 2 dimensions, or even. I mean, I am just giving you examples in 2 dimensions because you can draw things in 2 dimensions and imagine what they look like. I can have my Dirac deltas arranged in this way here, this funny way. Okay, so basically it's like moving along oblique lines, and in that case the Q matrix will be Tx and 0. So basically the Q matrix is Tx and 0. So we have 2 vectors of periodicity. One of them is that you move here by Tx, and the other is that you move not orthogonally but obliquely like this, and you move Ty horizontally and Ty vertically. So you can have a Q matrix that looks like this, and the pattern of your Dirac deltas will look like that. So once you leave, so we are talking about, in 1 dimensions, basically the Dirac deltas are a train of Dirac deltas. The only thing that you can change is the separation between the Dirac deltas, and that's it, which means, you will sample every, how many seconds? You will sample every second, every millisecond, or what? In 2 dimensions, you can play with the locations of the Dirac deltas. You can do this, which is like sort of the easiest sampling pattern. You can have Dirac deltas that are, that are on a rectangular lattice, rectangular grid, and basically they are spaced horizontally by tx, vertically by ty, and that's it. But you can do other things. Okay, you can do other things, and so your Q matrix does not have to be diagonal. It can be something like this. And perhaps in the next lecture why should you do something other than rectangular sampling? It may actually be more efficient to do something like this. Okay, so we should open the door for basically playing with the pattern of sampling in multi-dimensions. So again, sampling in one dimensions. Okay, you have a function. You pretend as if the function is multiplied by Dirac deltas, and in one dimension you just we are talking, of course, about uniform sampling. You just need one parameter to specify your sampling lattice. I mean, your lattice is just one dimensional. So you say, okay, the separation here is TS or delta or whatever you want to call it. That's it. In two dimensions, and in more dimensions, you can have your pattern of sampling point. So basically, you have those Dirac deltas, you multiply them by a function, and you take samples from the function, but according to a pattern that can be a bit complicated. This pattern will be specified not just by a parameter TS, but by a matrix Q. It just needs to be an invertible matrix. And it can be funny. It does not have to be diagonal. Diagonal, it's the easiest case, but it can be something that looks like this. Now, the sampling patterns are characterized by their density. So again, if we go to, so suppose that we are taking those samples from a two-dimensional, so suppose that you have a continuous two-dimensional signal, I mean defined continuously in terms of T1 and T2, and you want to take samples from it. Okay, so you ask the question, how many samples do I take the unit volume? And of course, in two dimensions, this will be unit area. In one dimension, we ask this question, how many samples per unit time? It is 1 over TS. If you sample every TS, then in one dimension, then the rate of sampling is Fs equal to 1 over TS samples per unit time. In two dimensions, now, how many samples per unit area, given the two dimensions T1 and T2? Again, that for images, they are not actually time dimensions. They are the X and Y of the image. Again, you can show that basically the sampling density, which is like the Fs that you are used to, is given by 1 over the magnitude of the determinant of Q. Okay, because, I mean, what is this thing? You basically take a fundamental cell, What is the volume of the fundamental cell? It's basically the magnitude of the determinant, and so you take one sample per fundamental cell. Okay, so it is 1 over the absolute determinant of Q. And this will be important parameter. Why? Because, like, what if you have, a band limited signal, and, it would be nice if you can sample that signal without problems, without distortion, without aliasing, with the minimum possible density, right? Because, you can take many samples from a signal, but this will overwhelm your processing and storage capabilities. So you can play with the patterns, and again, this will become clear in the coming lecture. But this is an important part. So sampling in multiple dimensions is cool. It is something that you have freedom. That is not in one-dimensional sampling is boring. It is just a lattice specified by a positive number. The separation between two successive samples. That's it. In multiple dimensions, you can play with the pattern, and you can specify any adequate periodicity matrix, and you will do sampling with basically 1 over determinant Q. So to understand how sampling works in multiple dimensions, we will need to take the Fourier transform of a Dirac deltas. So you have Dirac deltas defined at those points, or generally in the n-dimensional space. So what will be the Fourier series of this train of Dirac deltas? What will be the Fourier transform? So those will be like generalizations to what we typically do in one dimensions. We will ask what will happen, and guess what? The results are not surprising. You know, Dirac deltas in the time domain will be Dirac deltas in the frequency domain. Like those Dirac deltas, if you take their Fourier transform, they will be Dirac deltas separated by 1 over Ts. Okay, so something will happen here that will be related to the inverse of the Q matrix. Okay, so very cool stuff. So next time we will basically continue this and talk more about the sampling of band limited signals. What I'm trying to do is like I'm trying to mimic what you typically do when you study sampling in one-dimensional signal and map it to multiple dimensions. Okay, what is the difference here? The difference, again, you have now much more degrees of freedom, and you can get like very nice results, as we will see in the next lecture. Thank you very much, and talk to you.